Hello, I'm Caroline, welcome to my channel. In this video I'm going to take a look at this book, TK Eyewitness Science, a brilliant visual guide to science introducing the fascinating worlds of physics, chemistry and biology. So let's just dive straight in. Changing the world. Sometimes scientists discover that what they once thought to be true is in fact wrong. In 1543, Nicolaus Copernicus announced his discovery that would turn people's view of the world upside down. Until that time, people believed that Earth was at the centre of the universe, and everything else, including the sun, planets and stars, moved around it. But some planets slowed or sped up across the sky and even went into reverse. Copernicus showed that he could explain this behaviour if Earth was just one of several planets moving around the sun. Copernicus's discovery challenged facts that people had always accepted. There were more challenges to come. During the next decades, scholars in Europe looked again at established knowledge, especially from ancient Greek thinkers, and began a revolution in science. Feeling the pressure. Ancient Greeks believed that the Anemoi, or wind gods, controlled the seasons of the weather. In 1643, the Italian scientist Evangelista Torricelli became the first person to use science to forecast the weather. He built a barometer, a U-shaped column filled with a liquid metal, mercury. It measured air pressure, the force of the atmosphere pushing at Earth's surface. The air pushed at the open end of Torricelli's tube and made the mercury rise on the other side. The barometer showed that when air pressure was high, the day would probably be dry. Today's weather maps connect points of equal air pressure with lines called isobars. These help predict how the weather will change. This is a replica of Torricelli's barometer. Isobars show places with equal pressure on this map. Orrery showing planets revolving around the sun. A dangerous idea. In the 16th century, the Catholic Church controlled much of Europe and insisted that Earth was at the centre of the universe. Anyone contradicting the Church's belief, or even making a model or orrery of the planets moving around the sun, could be jailed. Copernicus knew the risks and kept quiet about his discovery until just before he died. The dead tell no lies. The Roman physician Galen was the established authority on human anatomy, the study of body structure for centuries. In the 16th century, the Belgian physician Andreas Vesalius began dissecting human bodies to to examine anatomy. He made highly detailed drawings of the body inside and out. Vesalius published his work in a book known as De Humani Corporis Fabrica, Fabric of the Human Body. His pictures were the first accurate record of human anatomy and corrected errors in much of Galen's work. Getting even. Greek thinker Aristotle had said that heavy things fall to the ground faster than light objects. However, in the 16th century, a young scientist called Galileo Galilei proved Aristotle wrong. Galileo dropped 2 cannonballs, one large and one small, from the Leaning Tower of Pisa, Italy. He noted that the balls fell evenly and hit the ground at the same time. He realized that objects fall to earth in the same time, whether they are heavy or not. Near side of the moon. Tycho crater, one of the moon's features picked out by Galileo in his drawings. Pointing north. For centuries it was well known that a swinging magnet always pointed in the same direction, north. In 1600, William Gilbert explained why. Any small magnet is attracted to a much larger one. Earth itself. He proved this idea by making a terrella, a model of Earth, out of a spherical magnet. By moving a smaller magnet around the surface of the terrella, Gilbert showed that the little magnet always swung towards the terella's north pole. Gilbert suggested that under Earth's rocky crust, the planet was made up of a giant ball of iron, which produced magnetism, a terrella. Seeing further, about 400 years ago, merchants in Venice, Italy, used telescopes to watch for their ships approaching the city Galileo, who lived in Venice at that time, built his own powerful telescope and used it to magnify the night sky. He was amazed to see that the moon was covered with mountains and craters, like a smaller version of Earth. He studied these features and made detailed drawings. Galileo also found that Jupiter was orbited by not 1, but 4 moons. This was the first direct evidence to support Copernicus's research. Not everything in the universe evolved around Earth. From magic to method. The word scientist was invented just 180 years ago. Until then, researchers were known as natural philosophers or alchemists. These people didn't use modern scientific methods. Most alchemists believed in magic, and many of them searched for potions giving superhuman powers. Alchemists had their uses. They discovered new dyes and ways to make valuable perfumes. As they searched for other useful substances, alchemists began to keep records so they could repeat procedures. They also used experiments to test ideas. Slowly, alchemists were beginning to work like scientists do today. This is a 19th century painting called The Alchemist. The last alchemists. Some of the greatest figures in the history of science were alchemists. Isaac Newton, who explained how gravity works, was an alchemist, looking for magical ways to turn lead into gold. Newton's friend Robert Boyle did similar research, but in 1661 he wrote a book called The Skeptical Chemist about how the behaviour of metals, gases and crystals could be explained using science instead of magic. Hocus pocus. Alchemists were the first people to attempt to explore what the world was made of. Most of them searched for the philosopher's stone, a substance believed to turn common metals into precious ones, or the elixir of life, which could supposedly make people immortal. Alchemists kept their work secret to prevent others from stealing their ideas. An 8th century Arab alchemist, Geber, recorded his results in a code that was meaningless to others. The word gibberish comes from his name. In the lab, the apparatus used in an alchemist workshop would be similar to a modern chemist. Bell jars collected the gases released, while any liquids produced in the experiments dripped from the spout of a retort. Hot gases were made into liquids by running them through a cooling condenser. Alchemists stored liquids in test tubes and retorts and used burets to measure liquids to the exact drop. Simple clocks, such as a sand timer, made sure that mixtures boiled for the right length of time. A retort held liquids, a sand timer, a bell jar, condenser, a burret, a pestle helped to grind substances, test tube, and a mortar held substances to be ground. A new way. In 1620, the English philosopher Francis Bacon set out a new method for research in a book called Novum Organum. He believed that thinkers should question the natural world and follow a specific method that included observation, suggestion of a theory, and experimentation. He stressed the sharing of information using simple language so that more people could understand and learn. This is the basis of the modern scientific method. Looking closer. People are limited by what their eyes can see. To see more, scientists invented machines to detect things that are too small or too far away. In 1665, Englishman Robert Hooke used a simple microscope to take a closer look at insects and plants. He found a tiny world full of detail. In the 1670s, the Dutch lensmaker Antony van Leeuwenhoek made a better microscope. Looking through it, he became the first person to see bacteria, which he named animalcules. Microscope is focused by screwing the tube up and down. A bulb filled with water concentrates light. Oil lamp provides light. Lens focuses light. Object being studied. Beating of the heart. Doctors once thought that blood was made continuously by the liver and heart before being pumped into the body, where it was used up. In 1628, the English doctor William Harvey carried out experiments that showed that if this were true, a person would have to make 250 kilograms or 550 pounds of blood a day. He showed that the body had a fixed amount of blood which circulated away from the heart in arteries and then returned in veins. Harvey's drawings show valves in the veins that stop blood from flowing backwards. The simplest answer. Occam's razor is a rule that helps scientists form ideas. Named after 14th century English thinker William of Ockham, it says that the simplest answer is most likely the correct one. When mysterious patterns of flattened crops appeared in fields in the 1970s and 1980s, some suspected that these crop circles were made by freak weather or even alien spacecraft. Using Occam's razor, however, the best explanation is that they were created by people as practical jokes. This turned out to be true. A new order. Few scientists make a discovery that fundamentally changes science, but Isaac Newton did just that. In the 1680s, he produced a series of laws that explained how things moved. Newton's most famous achievement was a discovery of how gravity worked. Gravity is a force that pulls masses together. The pull of larger bodies, such as Earth, is much stronger than that of smaller ones, such as apples. Newton described the force using mathematical calculations, which showed that a falling apple and an orbiting moon both move according to the same set of rules. Newton's laws of motion provided a new way to understand and investigate the universe. Down to earth. Newton is said to have figured out the way gravity works after seeing an apple fall from a tree. He suggested that every object has a pull of gravity. While Earth pulls on an apple, the apple also pulls on Earth. Because Earth is much heavier, its gravity is also stronger, so the apple accelerates towards Earth, while Earth hardly moves at all. Seeing the world. Sailors once used a sextant to measure the angle of the sun, moon, or a star above the horizon. This knowledge, combined with a ship's almanac, a set of tables, allowed the sailor to calculate the ship's latitude, its position north or south of the equator. From the 1770s, ships have carried almanacs, which predict the time when certain heavenly bodies will be at their highest point in the sky that day. This is thanks to Newton and other scientists, showing how the objects move in space. Swiveling mirror targets a heavenly body, a fixed mirror, a handle, light enters through the telescope, the eyepiece, arm moves with mirror to show angle, user reads the angle on the scale. The speed of light. In 1676, the Danish astronomer Ole Raymer measured the speed of light using Io, a moon of the planet Jupiter. Newton's laws of motion predicted Io's motion. It is hidden when it moves behind Jupiter. But Raymer knew that at the exact times Io would reappear. However, he found that the moon appeared 10 minutes late, the time its light took to reach Earth. The delays got longer as Earth orbited away from Jupiter. Raymer calculated that light travelled at 22,000 kilometres, 137,000 miles per second, only 25% slower than the true value. Floating in space. Why are astronauts weightless? Newton's laws predict that Earth's gravity gets weaker with distance, but never dwindles to nothing. Gravity is the force that holds a spacecraft in orbit around Earth and stops it escaping into space. Astronauts inside the spacecraft become weightless because they are orbiting with the spacecraft, in effect always falling towards Earth. They train for life in space inside a special aircraft that goes into free fall for a few minutes. Just like an orbit, everything inside becomes weightless. Astronauts practice the weightless environment of a training aircraft. The final push. Every object has momentum, calculated as the object's mass, multiplied by its speed. Heavier and faster objects have greater momentum, while stationary objects have zero momentum. When a moving ball hits a stationary one, it stops, but the combined momentum of the two balls it conserved or stays the same. A force from the first ball pushes the second one, making it move away with equal momentum. The balls in Newton's cradle do this. The momentum of the swinging ball passes through all the others until it arrives at the farthest ball, making that one swing away. Wire. Balls at rest transfer momentum to the final ball, and the final ball begins to move. The age of accuracy. Newton's laws describe the universe working like clockwork. Everything moved in a way predicted by his principles. Designers could use precise forces and masses to make even more accurate machines. Clocks were no exception. They used rocking pendulums to beat out the seconds. It was essential to know the time at sea because the time of sunrise told sailors their longitude or their east-west position on the globe. However, pendulums did not work on ships because the motion of the waves affected their swing. In the 1760s, spring-powered clocks called marine chronometers built by John Harrison were the first to maintain position on the oceans. This is Harrison's chronometer. Fly them to the moon. When, in 1961, US President John F. Kennedy ordered NASA to put astronauts on the moon before the end of the decade, there was a lot of work to do. But one job had been done already by Isaac Newton. His laws of gravity and motion told NASA scientists exactly how much force a rocket would need to send a spacecraft on a path to the moon. The Saturn V rocket would have to be the most powerful launcher ever built. It propelled a series of Apollo spacecraft to the moon between 1969 and 1975. And nothing bigger has flown into space since. Scientific method. Modern scientists work by following the scientific method. They begin by asking a question. Next, they find out more about their problem by collecting information, which helps them come up with a possible answer to the question. This idea is known as a hypothesis, which is then tested with experiments. They design experiments that may or may not produce results predicted by the hypothesis. An unexpected result means that the hypothesis must be wrong. Scientists publish their results to let others know what they have found. Other scientists repeat the experiment to ensure that the original experiment was performed correctly. Question. Scientists question everything. For example, why is the tongue of a blue-tongued skink blue? Very few animals in nature have this colouring, and the rest of this chunky Australian lizard is coloured to blend in with its desert surroundings. Biologists have learnt that the skink uses the vibrant colour of its tongue to frighten away its enemies. Observation. Investigation helps scientists form better ideas. Just 100 years ago, some scientists thought that the planet Mars was covered with canals. They claimed that this was evidence of an ancient Martian civilization. It was only when the first spacecraft landed on the planet in 1976 that they found out that Mars was a lifeless desert. However, later probes sent to Mars found evidence that simple alien life might have existed there billions of years ago. The latest NASA rovers on Mars are collecting more information to test this idea. Camera looks at the area around the rover. Radio antenna sends information to Earth. Solar panels collect energy from sunlight to power the rover. Experiment. Scientists have known for centuries that Earth spins around every 24 hours. That's how they explain why the sun rises and sets each day. However, no experiment directly demonstrated Earth's spin until 1851, when physicist Léon Foucault set up this giant pendulum in Paris. The pendulum swings in a fixed plane. It just sweeps back and forth and never swings in other directions. However, after swinging for hours above the dial, it seemed as if Foucault's pendulum was moving clockwise. It was actually the dial that had rotated anti-clockwise beneath it. The dial was moving as Earth rotated, while the pendulum kept swinging in its fixed plane. At last, here was evidence that the world turned. pendulum swings freely in one vertical plane above the dial. Markers help to measure the angle by which the plane of the pendulum's swing rotates. Dial rotates in an anti-clockwise direction in the northern hemisphere. Analyze results. Every experiment produces data, a set of measurements, numbers, or patterns that has to be analysed to find out what it means. This scientist is analysing a type of data that shows a person's DNA, which contains the person's genes, as a unique pattern of stripes. People with a stripe in the same position might possess the same gene. Scientists studying data like this have found that most people suffering from a certain disease of the skeleton share a gene called B27. However, most people with this gene do not get the disease. The disease could actually be caused by another gene sitting close to B27. So if you have the disease-causing gene, you will have B27 as well. Researchers continue to analyze genetic patterns to pinpoint this faulty gene. Repeatability. Scientific experiments must be repeatable so that the results can be verified. In 1989, two scientists claimed that they had discovered cold fusion, a method of generating nuclear power using the apparatus seen here. However, when other scientists conducted the experiment, they found that the system did not work. The claims of cold fusion had been untrue. Sharing knowledge. Scientists tell as many people as possible about their discoveries. Their colleagues check their work, and if they disagree with the results, they say why. Others agree and use the data to develop and test their own ideas. However, science sometimes hits the headlines. During the Biosphere 2 experiment in 1991, scientists invited photographers to cover the event. Scientists locked themselves in a giant isolated greenhouse for 2 years to test ways of being self-sufficient. Inspiration. Scientists are often inspired by discoveries made by others. In 2010, the biologist Craig Venter decided that people had such an understanding of how genes control living organisms that he could build an artificial life form. He chose a tiny life form called a bacterium and removed all of its natural genes. He put together a series of artificial genes and placed them inside the bacterium. The modified bacterium lived and reproduced normally. It is similar to the mycoplasma bacteria seen here. And this is where I'll end the video, and I hope you enjoyed it, and if you did, please join me for another one soon. Bye.